Section 4.2, average velocity and instantaneous velocity. Once again, taking a look at how these concepts we've already seen work in 2 dimensions. So our average velocity is just going to be the displacement divided by the time. It's the same definition as before, but now there's a little arrow on top of the v and on top of the displacement. These are now vectors. The direction does matter. So we can, just as before with displacement, we can write it in terms of the components, in terms of the change of the x, the y, and the z. And so we could break this down very nicely as shown, so that you're just looking at how the displacement in each direction divided by that time interval influences the average velocity in that direction. So let's look at an example of this in practice. So it says a particle moves through displacement 12 meters I hat plus 3.0 meters k hat in 2.0 seconds. What is its velocity? Well, if we want to find the velocity, right, we need displacement divided by time. So we can divide each of these numbers here in the displacement by the 2 seconds, and we'll have our final answer. So that is what is shown here, that we take the displacement divided by time, so the 12 divided by 2 becomes 6.0 meters per second. The units also go through there. And then 3 becomes 1.5 meters per second k hat. And that gives you the average velocity over that time interval. Now, we also have instantaneous velocity, right? This is the velocity at a single instant or point in time. And that's where we take look at the average velocity and limit. Look at the limit as that time interval shrinks to 0. And that gives us that instantaneous velocity is just the derivative of the position with respect to time. So dr dt. So if we want to visualize these, right, displacement and instantaneous velocity, we could imagine this bead on a hoop on a wire as it's following this path. That helps to understand why it follows this curved path. And so it has a position 1 and a position 2, which we could draw these position vectors r1 and r2 to locate those 2 positions. Then the displacement is just r2 minus r1, which mathematically would, by vector math, give you this arrow that is pointing from 1 to 2. The shortest distance between the points. Notice it doesn't follow the curve around. It just is the shortest distance between those 2. Now, for instantaneous velocity, it's not pointing to where it's going. So it's not going to point towards point 2. At point 1, the instantaneous velocity vector is always tangent to the path. So if you're following this curved path, you can draw a tangent line, as they've done here. Try and do one that's a little more accurate than just trying by hand. So you can draw a tangent line to the curve, and that gives you the direction of the instantaneous velocity at that instant. And you could break it down into an x component and a y component that, okay, in this instance, it's pointing mostly to the right in the x direction, but it is also going up a little bit. At another instant, it'll be going down again. And so this just gives you at that particular instant which way the velocity is going and the size of it, how much velocity there is there. Right, so again, writing this bullet point out, the direction of this instantaneous velocity is always tangent to the particle's path at the particle's position. It's a really nice synopsis. So in unit vector form, rather than writing that derivative out, we can write it as d dt of each of those scalar components, x, y, and z. And so we get that the velocity vector is dx dt I hat plus dy dt j hat plus dz dt k hat, which means we could also write our velocity vector as just being a combination of an x component of velocity, a y component of velocity, and a z component of velocity. That's what we saw on the last slide, where we saw that there was this overall velocity that was going up and to the right, and we could break it down into an x component, which would be our vx. That's a scalar, so we could add in the I hat, and then also a y component of how much that is going up, which we could label as v sub y j hat. So note that the velocity vector isn't from point to point. It doesn't say that it's going to later be at point 2. It just shows at this instant, it is going in this particular direction, it's going this fast. Okay, so with these ideas, let's take a look at a checkpoint now. So it says the figure shows a circular path taken by a particle. If the instantaneous velocity of the particle is v is equal to 2 meters per second I hat minus 2 meters per second j hat, through which quadrant is the particle moving at that instant if it is traveling A, clockwise, and B, counterclockwise around the circle? For both cases, draw V on the figure. All right, so I want you to think this through, come up with an answer for parts A and B before you move on. So go ahead and pause the video. All right, did you do that? I'm hoping so. Gonna trust so. So let's take a look at this. It gives us the velocity of the particle is plus 2 meters per second I hat minus 2 meters per second j hat. We can break this down. This tells us the x component is in the positive I hat direction, and then the y component is in the negative j hat direction with the same magnitude. Right, they both have a speed of 2, both directions have a speed of magnitude of 2 meters per second in speed. All right, so these are my two components for my overall velocity then. I'm going to combine them to get that the overall velocity vector is pointing down and to the right. So that is my overall velocity vector. Now, on this circular path that we're following, we know that we can find the instantaneous velocity by drawing a tangent to the curve. So where on the circle can we draw a tangent line that follows this path, right, being down and to the right? Well, there's two possible places, right? Notice if you draw tangent lines going all around here, right, you could keep drawing them until you find one that looks about right. And it turns out there's two here. So there's one in quadrant 1, and there's another one in quadrant 2. Those have the right direction. Now, we here don't want it to necessarily be going up and to the left. It specifies that we want it to be going down and to the right from that midpoint. So I've drawn a little too much here. But how do we know which it is between these? Well, that depends on if we're going clockwise or counterclockwise, right? So let's take a look here. If we are going clockwise, that means we're coming around the circle like so. And that means, notice at quadrant 1, we would, at that instant, be going down and to the right. Let's make this a little thicker. At quadrant 3, if we're moving clockwise, we would be going up and to the left. So it wouldn't quite work there, right? So that tells me for part A, we would want quadrant 1. Now, what about if we are going counterclockwise? Well, if we're going counterclockwise, then notice in quadrant 1, we'd be going the wrong direction where the tangent line is. So that's not so useful. But over in quadrant 3, that's now the perfect direction that we would match up with that point. So for part B, it would indeed be quadrant 3. All right, hopefully this helps to highlight this idea of instantaneous velocity and how you can use the tangent to note the exact direction of the velocity at that instant and how it matches up. So here are the answers. Clear all the drawings to get them out of there. And it matches what we found, that part A is in quadrant 1. Sorry about that, with it drawn as shown, and part B is in quadrant 3 with the velocity vector drawn as shown. So if you have questions, please do ask. I'd love to dialogue further. This brings us through velocity, and I'll let you think about what will come in the next section after position, displacement, and velocity. What do we have left?